Welcome to Pomodoro Joe for Friday, August 11th, 2023. Today we're doing LeetCode problem 518, coin change 2. This is a medium problem. You are given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the number of combinations that make up that amount. If that amount of money cannot be made up by any combination of the coins, return 0. You may assume that you have an infinite number of each kind of coin. The answer is guaranteed to fit in a signed 32-bit integer. All right. So you may have noticed I've already done this. I actually didn't like the video I recorded, so I'm doing it again. So for this one, we're given a list of coins of denomination. So we have like a penny and a 2-cent and a 5-cent coin. And we're trying to find a total of 5 cents. Or you could call these dollars, $1, $2, $5. And you're trying to find $5. So you could have 5 of the ones, or you could have 3 ones and a 2, or you could have 1 1 and 2 2s. So that's 3 different ways, or you could have just a 5. All right, and that seems to be right. We've got 4 different ways of doing that. All right, so let's put 25 minutes on the Pomodoro timer, and we will get started. All right, so for this one, for this type of problem, where we're building up to some amount, there are 2 general types of solutions for this. One will be a dynamic programming solution, and the other will be a recursive solution. So let's start with the recursive solution, and then if there's time, we'll go to the dynamic programming solution. All right, so we'll have some function in here, change recurse. All right, and for this, we'll take a remaining amount, however much we have left to try to make. So the remaining amount. And then with every recursive solution, we always need our base cases. So what are the different base cases for this? There are 2 basic ones. If we reach 0 exactly, that means our coins added up to our amount exactly. So if our remaining amount is 0, well then we can return 1 because we found one way for all of our coins to add up to exactly our amount. Now if the remaining amount is less than 0, that means we've overshot and we don't have a way to make our amount. So in that case, we return 0. We weren't able to make our amount exactly. Okay, so now we get to our recursive cases. Essentially, with our recursive case, we go through every coin. We can reduce our amount by the amount of that coin. So essentially, if we had a pile of coins, we assume we start with a pile of coins of our amount. We'll remove 1 coin. That leaves some smaller amount remaining. If we only knew how many different combinations there were to make that smaller amount, then we know how many combinations we have to make this amount. All right, that seems pretty straightforward. So for every coin in our coins, we'll just subtract this coin from our pile of coins, from our amount, and then we'll find out how many combinations there are to make that smaller amount. So let's see. Let's have some new amount. It's more like the new remaining amount, but I'll just say new amount. That's going to be our remaining amount minus this coin. Now our result will increase. Let's see, we don't have a result yet. So let's have our result out here, start at 0. Now, however many ways there are to make this new amount, we can increase our result by that many ways. So essentially, if we had, let's say 100, and we removed a coin of 5. Now we have a remaining amount, or a new amount, of 95. If we know how many ways there are to make 95, then we can just add our 1 coin, our 5 coin, to that, and get 100. So if we know how many ways there are to make this new amount, then we know how many ways there are to make our result, or we can increase the number of ways to make our result by that. All right, so our result will increase by the number of ways to make this new amount, and that's just change recurse. New amount. Awesome. And then at the end, we just return our result. Okay, now out here, we do need to kick the whole thing off. So we will return change recurse with our initial amount. Great, this seems pretty straightforward. So we'll go through, grab our amount, and then for every coin, if we remove that coin from the pile, we have this new amount, a smaller amount. how many ways were there to make that amount? If we know how many ways there are to make that amount, then the number of ways to make our target amount is increased by that. All right, hopefully this all makes sense. Now, there is a problem with this, but I think the best way to illustrate that problem is just to run it. So let's run it and see what we get. Okay, so we pass 2, but we fail on 1. Now, why are we failing this one? What do we get? We get a 9, but they expect a 4. And we already kind of went through this one, and it is 4. So how did we get 9? So the problem we actually run into here is we're finding all of the different permutations of these coins, not the different combinations of these coins. So we'll have the same combination, 3 1s and a 2, but we'll be counting every permutations of those 3 1s and a 2. So we'll count 1 1 1 2, 1 1 2 1, 1 2 1 1, 2 1 1 1. They're all the same combination, but just in a different order. So that's why we're overshooting our count. Now, how do we solve for this? Well, let's just take one coin at a time. So let's have a coin index here. All right, so we have our coin index. Now, instead of going through every coin, we have 2 choices. We either use this coin or we don't use this coin. So that means out here we do have to start at coin index 0. Okay. So now we have 2 options. We use this coin, which is very similar to what we were doing with our reduction of our new amount. Actually, let's do that here, new amount. So that's going to be the remaining amount minus this coin. Actually, it's coins at this index. All right, and now we have these 2 options. Option 1. Actually, let's do the second option, the easier option. So result will increase by the recursive call. Let's not use this coin. We're done using this coin. We're moving on to the next coin. So this will be coin index plus 1 and the remaining amount. We didn't actually change our amount at all. We're just moving on to the next coin. So we're done using coin 1 and let's move on to coin 2. Same amount. Now the other option is we're going to use this coin, but we have an infinite number of this coin. So we'll use this coin, but we're actually not going to move on. We'll see if we want to use more of the same coin. So the same coin index, but now the new amount is our second argument. This is probably more confusing than the DP solution. So we'll run this, but I'll try to explain this better when we do our DP solution. Oh, and this is clearly an error. I wasn't taking into account that we might go out of bounds with our index. So let's actually put that up here. And we can swap this around. So if our remaining count is less than 0, or our coin index is greater than or equal to the length of our coins. Okay, hopefully this will fix that. All right, and we pass. Now I could submit this. I already know it's not going to run in the runtime that we need, but I'll go ahead and add a cache decorator here. And this should work, and it should run in the runtime that we need. Okay, so this works, but it doesn't do great. We only beat 21% for runtime and 5% for memory. Not a great solution. As you can see, I did this before, same solution without the caching. It had a time limit exceeded, so it's not going to work. All right, let's jump back here and see if we can do better with a dynamic programming solution. So this solution will be basically the same that we just did with our recursive solution. It's just going to take it from a different approach. We'll use the dynamic programming approach. Now with our recursive solution, we had some amount we were looking for. We removed some coin and we recursed on a smaller amount. So essentially we were saying, if I know how many ways there are to make some smaller amount, then I know how many ways I can make my target amount. And that's the same thing we'll do with our dynamic programming. So we'll have some dynamic programming here, and this will just be an array. And this array the index will be the amount that we're looking for. So the index will represent an amount, and the value will represent the number of ways, or the count. I'll call it number of ways. The value will represent the number of ways to make that amount. So it's very similar with our recursive solution. If we have some smaller amount and we know how many ways there are to make that, then we can determine how many ways there are to make our current amount. So let's start this at 0. So we don't know how many ways there are to make these, so we're going to initialize them with 0. And how many different amounts do we need? Well, we need to get to the index of amount. So we need to make amount plus 1 of these. Cool. And now our DP, we're going to start this off, our DP at 0. There's one way to do 0. We could have no coins, so there's one way to do that one. All right, now it's just a matter of going through and figuring out if we have some amount, how many ways are there to make some smaller amounts? All right, so we just need to fill up this array. So for every amount, I'm just going to call it AMT in range, and we have to go from 1, because we already have 0 covered. So we'll go from 1 up to our amount plus 1, because range is not inclusive. So now we're going to be filling up our array of amounts until we reach our target amount. Pretty straightforward. All right, so how do we fill this up? Well, we take our current amount, we subtract some coin from it, and that'll give us some previous amount. If we knew how many ways there are to make that previous amount, then we can add that to our current amount number of ways. All right, so let's see. For every coin in our coins, we'll subtract this coin from our amount. So we'll have some previous amount. That's just our current amount minus this coin. And now our DP at the index previous amount will tell us how many ways there were to make that previous amount. And if we know that, then we can just add this particular coin to that amount to get our new target amount. So the first thing I want to do here, though, is to make sure that this previous amount is not less than 0. So if the previous amount here is less than 0, we're not going to count this one. We'll just continue. All right. Now, if our previous amount is greater than or equal to 0, that means it's going to be a valid index in our DP here. So our DP for this amount can increase by the DP at the previous amount. And then at the very end, our result is just going to be stored in our DP at our amount. Cool. So this is pretty straightforward, right? Now, I can already tell you there is a problem with this, but we'll run it and we'll see if we can figure it out. Look at that. Very similar to our recursive case when we had a problem. We're reporting 9 when we should be reporting 4. Now, do you remember what the problem was with our recursive solution? It was that we were finding every permutation of our combination and not just every combination. And that's the same thing that's happening here. This is finding every permutation and not just every combination. And why is that? Well, for every amount, we're going through every coin. That means we're going through the same coins. We're going through 1 multiple times, and then 2 multiple times, and 3 multiple times. So we're going through every coin multiple times for every amount. Well, if the problem is that we're going through our coins multiple times, starting over from coin 0 each time, what can we do to only go through our coins once and yet still have the same structure here where we're going through every amount from 1 up to amount plus 1, or amount? Well, it's pretty simple actually. We can just swap these for loops. So let's go through every coin first and just find all the amounts that that coin can create. So we have essentially the same loops, just swapped in a different order. So this way we only go through each coin once. All right. Hopefully this makes sense. I know it's confusing, but let's run this and see how we do. Okay, so now we're passing. Let's submit this and see if we can pass all the tests. And we pass all the tests, and we do okay. We're at a 76% for runtime and an 89% for memory. So that's really good for our memory. Yeah, so this isn't bad. So yeah, I'm pretty happy with the solution. We can jump back and try to make some changes, but I don't think there's a whole lot we could do. We could do one thing super quick here. Instead of doing a continue, let's check to see if this is greater than or equal to 0. And then we'll do our DP. So we'll do it like that. That might save us a little bit. Let's find out. Not really. It's basically the same we had before. 76 for runtime and 89 for memory. So yeah, it's the same. Well, that's it for me. I had a little bit of a struggle explaining this one, but I hope you enjoyed it. I hope you had fun. I hope you learned something. I hope you can go out and write better code.